All right, looks like today we're doing Trig, lecture 2.8 and 2.9. And it's OASA 2A17. The student will determine whether an infinite geometric series diverges or converges. And if it converges, we will find the sum. This isn't really trigonometry. We're, again, as I said in past lectures, we're covering this because we didn't get to cover it last year in Algebra 2 due to the pandemic. So I thought we'd back up, hit it so you guys could see it, and onward through the fog. First thing I want to talk about is we're going to determine whether an infinite geometric series diverges or converges. Now we've talked about geometric series in the last lecture that we did. In the last couple of days we've done assignments pertaining to finite geometric series. Now we're going to talk about an infinite geometric series. That's a row of numbers that are added together that go on infinitely. And we're going to add those up if possible. Now intuitively it seems like it would be impossible. If you have an infinite number of numbers and you just keep adding more and more numbers, the idea of being able to add them all up seems impossible. But under certain circumstances it is possible, and I'm going to show you how to ascertain whether it's possible and then how to add up the infinite sum. So here we go. Determine whether an infinite geometric series diverges or converges. If it diverges, we cannot find the sum. Okay, so here's how you find it. Find the common ratio. 4 divided by 2 is 2. 8 divided by 4 is 2. There's our common ratio. We can see that. And if the common ratio, if the absolute value of the common ratio is greater than or equal to 1, then it diverges. And you cannot find the sum. Okay, so this one diverges. And what that means is if it diverges, this sum will just get infinitely large. Or if these were all negative numbers, it would go infinitely small. And we can't find the sum. However, in a situation like this, if we divide this one by this one, that would be 3 halves divided by 3 over 1, which would be 3 halves times 1 over 3. That would be 1 half. 3/4 divided by 3 halves is 3/4 times 2/3. That's 2/4, which reduces to 1 half. So our common ratio is 1 half. Don't forget that a fraction bar means the word's divided by. So you can think of 3 halves divided by 3 over 1, or 3/4. You can put it 3/4 over 3 halves. Divided by and a fraction bar mean the same thing. We found our common ratio. The absolute value of this is not greater than or equal to 1. In other words, it's less than 1, greater than 0, and therefore it converges and we can find the sum. Oops. See if I can spell the word converges. Now I want to talk to you about converges real quick, kind of give you an idea of what's going on. Converges. We say that the series converges, or we say that the series is convergent. Let's take a look at what converging series do. I'll glance at one, I'll make one up. 1 plus 1 half plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus so forth and so on. I'll continue this pattern infinitely. I'm multiplying each term by 1 half. I started with 1 and I'll do this forever. If we look at this graphically, take a look on the number line for instance, it might give you kind of an intuitive idea of what's going on. If this is 0 and this is 1 and this is 2, and I'm adding these numbers together, well, let's start with 1. If I was adding on the number line, I'd be right here. If I add 1 half to this, now I'm here, 1 1/2. If I add 1/4, I'm adding 1/4 to this, so now that's half of this distance is 1/4. If I add 1/8, I'm half of this distance is 1/8, so I'm adding 1/8 to 1. 1 plus 1/4 plus 1/2 plus 1/4 plus 1/8. 1 plus 1/16 to this sum now is going to be right here. If I add 1/32, it'll be half of this. And I can always take half of the distance between this number and the number 2. I'll get infinitely, infinitely, infinitely closer and closer and closer to the number 2. Never actually reach it, but the limit of this sum will be 2. And that's how we define the sum of the infinite series if it converges. It's the limit of the sum. And we can find what number it's approaching using a really easy formula, and I'll show you how to do that. But that's that's my attempt to give you kind of an intuitive idea of what we mean when a series converges. It gets infinitely closer and closer and closer to a specific number. It'll never quite reach it. But when we take the limit of what it's approaching, that's what we call the sum. That's how we define the infinite sum. So let's take a look at how we do this. Evaluate the infinite geometric series described. The first thing we have to keep in mind is that this formula right here will do all of the work for us. A sub 1 is the first term. R is the common ratio. We've been working with those in arithmetic and geometric sequences in series, and so we're familiar with these two. Plug this in here, and this will give us the number that's being approached by an infinite geometric series if we can determine that the geometric series converges. And we can do that by simply dividing the terms, and if the common ratio R is not greater than or equal to 1, in other words, if it's between 0 and 1, then we can say that it converges and we can find the sum, and this little formula right here will give us the sum. Plug in a first ratio here, first term here, common ratio there, do the arithmetic. So let's take a look here. In this case, this is being described to us. It tells us the first term and the common ratio. So I'm going to start with 3/2. You don't have to do this part, but this is just what it means. And I'm going to multiply it by 1/3. And I'm going to keep multiplying it by 1/3 and adding and adding and adding. So 3/2 plus 3/2 times 1/3 plus so forth and so on. But I want to just add this up. So here we go. The sum of this infinite series is equal to A sub 1, that's the first term, divided by 1 minus R. Okay, now we've got some arithmetic to do. I'm going to clean that up a little bit. This is 3/2 divided by 1 minus 1/3 is 2/3. You can think of that as 3/3 minus 1/3. So, and then we invert and multiply, leave this one alone. Invert and multiply. And we get 9/2. Or you could think of that as 4.5 if you want to. 2 goes into 9 4 times with a remainder of 1. These are both the same value. Okay. So if I were to start with 3/2 and then add 3/2 times 1/3 and then add whatever that is times 1/3 and just keep multiplying by 1/3, this infinite series that would be generated would approach 9/2 or 4.5 on the number line. We get infinitely close to that, and so that's what we call the sum. Closer and closer and closer. Let's take a look at this one. I want to find the first term. Well, I can find that by looking at it. I want to find the common ratio. 5/3 divided by 5/1 is 5/3 times 1/5 is 1/3. There's my common ratio. If I divided these two, I'd get it 1/3. If I divided these two, I'd get 1/3, because it tells me that the series is an infinite geometric series. It's definitely a geometric series, so I know that these r's are going to be the same value. So now that I have the first term and the common ratio, I just plug it into my formula to find the sum, and that is the first term over 1 minus r. A sub 1 is 5. over 1 minus r. And I just found r to be 1/3. Hopefully I did that correctly. 1/3 again. How about that? I never did check this to see if I got it right. I got my answer here. Let's see. Yay! 9/4. This is, oops, 5 over 1. I can do that. Over 1 minus 1/3 is 2/3. This is 3/3 minus 1/3 is 2/3. I'm just thinking this is 5 over 1, thinking of it as 5 over 1. So that I can invert and multiply a little more easily. This is 5 over 1 times 3 over 2. And that gives me 15 over 2. That's my sum. 15 divided by 2, well, 2 will go into 15 7 times with a remainder of 1. So we could think of this as 15 halves or 7 1/2. That's the sum of this infinite series. If I just kept multiplying by 1/3 and adding, multiply this by 1/3, I get this. So I multiply this by 1/3, and I do that forever. This board would have to keep growing and go off the edge of the planet, and I'd still be writing fractions. It'd leave the solar system, and I would still be writing fractions. It'd leave the galaxy, I'd still be writing fractions forever. We can find the sum of all these to be 15 halves, because these values will get closer and closer and closer on the number line to 15 halves, infinitely close. And so that's how we define the sum. Okay. That's the infinite sum. Let's take a look and see if I got it right now. Yay, 15 halves or 7 1/2. They're both the same value. Just two different ways of saying the same number. Let's take a look at this. This is written in sigma notation, or we can say summation notation. It's another way of saying it. Again, we've worked with these in the past. The general case of a geometric series in sigma notation is a sub 1 times r to the n minus 1. This is the general case. So I'm looking at the first term. This is a sub 1 right here. This is r right here. So I've got everything I need to plug into my formula. A sub 1 divided by 1 minus r. I've got that. I'm going to be using this formula. I'll write it down. The sum in general form is a sub 1 over 1 minus r. And I can see those two things in sigma notation. That's a sub 1 and that's r. So here we go. I'm going to plug them in. And this will be an infinite series, because what will happen is I'll plug in a 1. I'll do the arithmetic. I'll get a number. It'll be -8. That's the first term. And then I'll plug in a 2. Do the arithmetic and add that to -8. Then I'll plug in a 3. Do the arithmetic and add that to the sum. And I'll keep doing this infinitely. It's going to go from 1 to infinity. I'll never stop doing it. This will create an infinite geometric series. It'll converge. I know it converges because the value of r, the absolute value of r, is less than 1. So less than or equal to 1. No, less than 1, I'm sorry. Here we go. We're going to find this sum. A sub 1 is -8. 1 minus -1/2. That's -8. You can think of this as 2 halves plus 1 half. That's 3 halves. And I'll do this arithmetic. You can do this with your calculator, I suppose. -8 over 1 times, and I'm going to invert and multiply, 2 over 3. This will give me -16/3. 16, 1 times 3 is 3. And we can think of that. 3 goes into 16 5 times with a remainder of 1. Whoops, I forgot my minus sign. 3 goes into 16 5 times with a remainder of 1. So -5 and 1/3. Both of these have the exact same value. This infinite geometric series will add up to negative 16 thirds, or you could think of it as negative 5 and 1/3. They're the same value. Okay. That's how we deal with infinite geometric series, written in sigma notation, or you'll hear it called summation notation as well. So here we go. I'm going to ask to do the same thing. There's a sub 1 right there. Here's R. I can see that it converges, so I can find the sum. The sum is a sub 1 over 1 minus R. That is, you can think of this as 6 over 1 if you want to, over 1 minus 1/5. Well, that's 5/5 minus 1/5 is 4/5. Now I'm going to take this fraction, write it down, multiply it by the inverse. I'm going to invert and multiply. So this is going to equal 6 over 1 times 5 over 4. These will reduce. That'll become a 3, divide both by 2. This will become a 3. That'll become a 2. That gives me 15 over 2, if I haven't made a mistake, or 7 1/2. I hope that's right. I feel like I've made a mistake, but let's see. I didn't. Yay, 15 halves. What do you know? So there we go. This infinite sum, if I plug in 1, and then plug in a 2, and plug in a 3, and plug in a 4, all the way to infinity, which means I'll just keep going forever, that infinite number of numbers will converge to 7 1/2. They'll get infinitely close to 7 1/2 or 15 halves. So that's what we call the sum. Here we go. That, in a nutshell, is infinite geometric series. You can do this. Here's the key right here. This is the formula if it converges. And you find out whether it converges by finding the common ratio. If the common ratio is greater than or equal to 1, it diverges. That means it'll get infinitely large or infinitely small. You can't find the sum. But if it converges, if the absolute value of R, just make it positive, if the absolute value of R is between 0 and 1, it converges and you can find the sum. It'll get infinitely and infinitely closer and closer and closer to a specific number on the number line, so to speak. You can visualize it that way. Okay. You can do this.